So I want to discuss a particular problem, which is the longest increasing subsequence. And if you have not already done so, you should first watch the video that has to do with the longest common subsequence, because I want to talk about the relationship between these two problems. It turns out that you can sort of transform one problem into the other one. So the longest increasing subsequence is something where you are given an array of values, and you are wanting to find what the longest sequence of values in that array is. So as an example, one we'll return to later on, if I had the set of values 1, 5, 10, 2, 11, 4, 9, 6, 7, 3, and I wanted to pick out the numbers, the longest sequence I could get out of this list where they were continually increasing. I might look at how I could do that, and I believe it would be something like 1, 2, 4, 6, 7. Okay, so that I could get those 5 values as an example. So that's an increasing subsequence of the original one. And notice it's always going up 1, 2, 4, 6, 7. And I just at a quick glance, I don't think there's a better one that I could pick from this particular sequence. So that's the longest increasing subsequence problem. Now, there is an algorithm for this that is relatively efficient. It's basically an n log n algorithm, but there's a dynamic programming approach that's order n squared, and it's often been used in the past as sort of a way of describing how to do dynamic programming. It's a little weird to use it since it's not the optimal algorithm, but it is one that's there. And before I get to the n log n algorithm, which is actually not that difficult to code up, I want to talk just briefly about how LIS, which is what this one is related to the LCS problem. So just as a quick reminder, the LCS problem would say, if I've got two different arrays of values, so perhaps I have that one that I just wrote up here, and I have another array that has numbers like, 12, 10, 11, 4, 8, 17, 6, 2, 1. Okay, so we have something like that. Well, I want to find what the longest common subsequence is. So something where I can pick out a value from each one. So say 10 and 10, and 11 and 11, 4 and 4, maybe 6 and 6, and that might be it. I don't know if that's the longest or not, but there's a subsequence of length 4, and that's the longest common subsequence. It's a subsequence in both of these. Okay, so the LIS and the LCS turned out to be kind of related to each other. So we went over the algorithm, a dynamic programming approach for computing the longest common subsequence in the earlier lecture that had to do with strings. And what I first want to point out is that we can solve LIS using LCS. Okay, so if we have an LCS solution like we had before, we can actually use that to solve the longest increasing subsequence problem. And the way we do that is we take our array A, and then we have a new array that is sorted A. So we would set B equal to sort of A. Okay, so we take a sorted version of A. And what we get is that the longest common subsequence between A and B is the longest increasing subsequence of A. And that might not be a totally obvious thing, but if you think about it for a minute, notice that B and A both have the same size. So both of them have n elements. And since B is sorted, any subsequence of B is going to be in sorted order from smallest to largest. So it's going to be increasing. So by definition, B is increasing. And I'm going to assume that all of the elements here are unique just because it's easier. You can make adjustments if they're not. But if you imagine they're all unique, then everything in B is in increasing order. So any subsequence of B is in increasing order. And therefore, the longest common subsequence between A and B is going to be an increasing subsequence in A. It has to be because it's increasing in B, so therefore it's also increasing in A. And it's going to be the longest one possible. It's not possible to get any other subsequence that's longer than that. So this is kind of a cool idea, is if we already know how to do LCS, we can just use that to get LIS. So it's basically already been given to us. Now, one thing that's maybe a little bit less obvious is we can also use LIS to compute LCS. And here we do have to assume that the LCS elements are unique. It gets quite a bit more complicated if they're not. But this one's a little bit trickier to figure out. So if we have LCS, and we're wanting to find the longest common subsequence between two different series, what we can do is we can, first of all, so of A and B, we can first of all find the order of the elements in B. In other words, the index, so maybe instead of order, let's not say order, let's say the index of the elements in B. And if those elements are in A, then we replace them by the index in B. The other elements of A get replaced by by basically, we can either completely delete them from A, or we can replace them by a absolute min or max value. So something like infinity or 0 or whatever you want to use that would be there. Okay, so let me give a quick example of this. So let's say that we have, I'm just going to use something that's a permutation. These don't have to be permutations in general. But let's say that our list A is going to be the numbers 3, 4, 5, and I'll do all the numbers from 1 to 12 will be in here. So 12, 11, 6, 1, 2, 9, 8, 7, 10, and then B, I'll let it be 9, 7, 3, 5, 10, 11, 12, 2, 8, 1, 4, 6. So hopefully I did that right. And so the first thing I would do is I would compute what the index of everything in B is. So basically you can, if you're implementing this in practice, you can use a hash table to do this. So you mark what each value is in B. So I know in this case, I'm going to have all the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they actually go all the way up to 12. And I'm going to just do the index. So the index of 9 is 1. The index of 7 is 2. The index of 3 is 3. The index of 5 is 4. 10 is 5. 11 is 6. 12 is 7. 2 is 8. 1 is 9. And I feel like I skipped something here. Sorry, 8 is 9. I'm sorry, 8 is 9. 1 is 10. 4 is 11, and 6 is 12. Okay, so there's the 12 numbers. So now what I'm going to do is I'm going to convert A into this list of values here. And so basically what that's doing is it's saying, where is the equivalent value in B? Okay, so I'm replacing the actual number in A with where that appears in the B list. Okay, so notice if this is a hash table that I keep right here, okay, on average, it's going to be linear time to insert and to look up. So I've just had an order n operation in B, and now I'm going to have another order n operation in A, and then I would be able to apply LIS to A, and that would compute the longest common subsequence out of these. Okay, so if this is the case, let's convert this. So A, it starts out with 3. Well, 3 had the value 3. So I'm going to look everything up over here. So 3 had the value 3. 4 has the value, notice that's 11. So it would be 3, 11. 5 is 4. 12 is 7. 11 is 6. 6 is 12. 1 is 10. 2 is 8. 9 is 1. 8 is 9. 7 is 2. And 10 is 5. Okay, and that should be all of the numbers. Okay, and so now if I want to find the LIS here, well, first of all, let's look at these first two and let's find what's the longest common subsequence here. And this is one, it's small enough I can kind of look at it and see what they are. So I see I've got 3, 5, maybe I could do 11, but that might not be the best. Let's see about doing, yeah, maybe it is 11. The next one that's common is probably the 2, and then 8. Okay, so that looks like the longest common subsequence. It's length 5. Okay, so I'm going to just mark the equivalent ones here in blue. So it was this one, skip 1, 11, then skip 2, it was that one, then skip 1, and it's that one. Okay, and if I look at these same values right here, if I were to do the LIS in this, the longest one that I could have is 3, 4, 6, 8, 9. Okay, and again, what that is doing is remember that these are going to be the indices in B. That's what this transformed version of A is the indices of B. And so what I'm wanting to find is what's the longest increasing sequence of indices in B that matches up with A, and that is going to be my longest common subsequence. Okay, so the important thing to this point is to realize that LCS and LIS, you can transform from one to the other, and it's not that difficult to do. Transforming LIS to LCS is n log n. It's an order n problem to switch from LCS to LIS. Okay, so given all of that now, let me go through the more efficient version of solving LIS in more of an n log n time. So the basic idea here is that we're going to keep track of what the longest, well, I'll keep an array, let's call it L. So I'm going to keep track of L, and L of I will be the largest value so far in a sequence of length I. Okay, so in other words, if you have an increasing sequence, so if I have a sequence like 1, 2, 3, okay, so this would be L of 3, and it would have the value 3. And if the sequence was 1, 2, 5, then it says the longest sequence of length 3 had the largest value of 5. Okay, so L sub I is going to be the value of the largest thing of that sequence. And the largest sequence of length 2 that I might have in this case was 2, right? That's the largest thing that I could have, size 2. Largest of 1 would be 1, okay? And remember, or I say, what we're going to do is we're always wanting to keep kind of what's the smallest of these largest values. So we want to minimize this maximum value. It's probably easiest to see this. This is actually, I don't want to make this overly complicated because it's actually a relatively easy thing to do and to keep track of. So let me do an example here, and I think that will illustrate better than talking through details. So let's say that we have a sequence 1, 5, 10, 2, 11, 4, 9, 6, 7, 3. Okay, something like that. Okay, and what we're going to do is we're going to go one by one through this list, through the array here, A, and we're going to keep track of L along the way. So we're going to keep track of kind of what the longest values of L are. So we start out, and L, we're not even going to have L1 because there's nothing even of length 1. So basically, there's no L's. So L does not exist at first. When I come to the first element here, well, obviously, I now have something of length 1. So what I can say is that L of 1 is equal to 1. And I'm going to build up additional L's as I go along. Now I come to the next element, 5. And what I'm going to do is I'm going to search through here, and I'm going to find basically which value am I just bigger than? So is 5 bigger than something in the list? Well, sure enough, it's bigger than the 1. And so we're going to make a choice each time. And the choice that we always have is if it is at the end, then we are going to create a new L sub I, one longer than before. Value is that number. So if it's at the end, if it's not at the end, if it's in the middle, we will see if it replaces, or see if it is smaller than the existing value. So again, I need to show you how this works to illustrate it. Okay, so when we come here to 5, now what we're going to do is I'm going to create a new one, and I will say L of 2 equals 5. Okay, and so what this means is that there is a sequence of length 2, and that sequence of length 2 has a final value of 5. So there's some number before it, and the largest number at this point is 5. And so you can kind of think what that means is if I come along with something bigger than 5, I can tack it on to the end of that. Okay, and likewise, if you kind of look at this, there is a sequence of length 1 that the largest value is size 1. And so if I have something that comes up between 1 and 5, I can actually improve on that, on the length 2 one that I have here. Okay, so let's try the next value. So the next one is 10. Okay, so what I would do is I would do a binary search on my existing list of L values. And in this case, there's only 2, but if I had 100 of them, I could do a binary search on that group of 100, and I could find where 10 comes. Well, 10 is going to come right after the end. And so since we are at the end, we're just going to add on to L. And so we will just say, we'll get one more L, and we'll set that equal to 10, and we're done there. Okay, so now is where it gets a little bit more interesting. So now we have the value 2. If I do a binary search on this, I find that the next biggest value is this one. Okay, and I am not at the end, so that's not the case. I am somewhere in the middle. And so since 2 is smaller than 5, I am going to replace 5 with a 2. Okay, and so what I want you to see right now is notice that this L list here, this is not the longest increasing subsequence. Notice that 1 to 10 is not a subsequence here because the 10 comes before the 2. Okay, what this means is there is a subsequence of length 1 that the greatest value is 1. There is a subsequence of length 2 that the greatest value is length 2. There is a subsequence of length 3 that the greatest value is 10. It's not saying that this is the subsequence. It's just saying that that's what the largest value in one of that length is. Okay, that's not clear. Think about that for a minute before going on. Pause and think about it. Okay, let's go on to the next one. So we have 11. If we do a binary search, it comes out past the end. So we create a new one. L of 4 equals 11. The next value is 4. If I do a binary search on this, it comes out right at that point. And since 4 is smaller than 10, it will replace 10. Okay, just like that. The next one that we come to is this 9. Again, since 9, if we do a binary search, it's going to come out at that point right there. Since 9 is smaller than 11, we go ahead and we replace the 11 by the value 9. Okay, and so now what this means is we have a sequence of length 4 where the greatest value is 9. We have a sequence of length 3 where the greatest value is 4. And so, okay, now we come to this 6, and so we say 6 ends up right there in a binary search. That's the next biggest number. And so again, we're in this middle condition. So we are going to replace the 9 by a 6. The next thing we have is a 7. And so we will add on L of 5 equals 7, just like that. And then we finally have one that is 3. So when we do a search here, that's going to come here. And so this value will be 3. Okay, and so we're done now. We've gone through the entire list. Notice that each step here, we had a total of n steps, and in each one we were doing a binary search on this list. So we have n log n total time. So that total time was n log n. The end result that we have is we say we have an increasing sequence of length 5, and actually the answer is 7. Now, if we want to actually reconstruct the longest increasing subsequence, then what we want to do is every time we come to a number here, we want to say what the number before it was. Because notice 1, 2, 3, 6, 7 is not, this is not the LIS here, right? That would go 1, 2, 3, 6, 7. So it's like going backwards. So we can't do that. That's not allowed. But instead, what we could have done along the way is every single time, each time we visited a number, we would say, okay, what's the previous thing in the sequence before it? And we can just update it there. And that would just be a constant time addition onto the end of all of this. Okay, so that's the longest increasing subsequence algorithm. Again, it's an n log n version. And if you remember, we said that you can use LIS to compute LCS if you want to. So you can actually use that n log n algorithm to compute LCS, even though it's instead of doing the dynamic programming approach that we described before, although probably the dynamic programming is a little bit more intuitive, at least at first glance. Okay, and I should mention again that transformation that we talked about, LCS to LIS, it does assume that you've sort of got unique indices here. If you have repeated things, that's going to be a problem. So just keep that in mind if you want to try to do that transformation.